I'm coming from the image analysis and microscopy side. So for us, it is important, or it's interesting to put in or put challenging and interesting material into the high content screening machines. So we are interested in the science, not necessarily in the assay development. So we are interested to push the boundaries of what we can do, what we can image. And since we were interested in a few diseases, as I'm part of the medical faculty, it happened that we were interested in both ciliogenesis, which is related to cancer phenotypes, as well as neurodegeneration, where we have been investigating a little bit on how microautophagy is happening at synapses, which is supposed to support protein turnover at these synapses. We have been starting to look for ways how we could analyze these questions, and therefore we started investigating things like giant unilamellar vesicles, where we could actually look into how crowding, how different proteins affect tubulation and how they deform these membranes of these artificial samples. As such, it's an interesting way because it liberates us from using standard assays or standard cell types or these type of things. It's way more fun to do as well, just to do new things on our analyzers and see if we can get something going, and the reward is that we actually see new results and new science happening. Similar was with the cilia, where, at least to my knowledge, no one has actually looked into ciliogenesis in a high content environment, while we actually found out it's relatively straightforward, and but however, making it happening was quite fun to do. The challenge is, I think, the general challenge of quantitative biology, because in an academic setting, what we're doing is we want to derive new information. We want to understand how mechanisms work. In order to do that, we need to go about and not only measure a few images, that's how we did it in the past. Now we need to do that on a way more quantitative level. Screening is actually a way or a means of getting there, because with higher number of images and higher confidence, this allows us to image not only a one-time or a one-trick pony. We actually get more confidence about what is going on, and we can use it as a resource to reanalyze our assays again and again for hidden phenotypes, for multiple populations within our area of investigation. And the challenge was more like getting the people convinced that this is, I think, the best new way forward to do so. While I'm actually convinced, it always is, of course, important to communicate that well. And I think the biggest challenge is the communication and not necessarily doing it. Yeah, you asked before what's the challenge within VIB, and now you asked about LiMoNe. The reason why these potentially confusing different acronyms exist and are associated with us and what we're doing is because we have a dual affiliation. On the one hand side, I'm affiliated with the VIB, which is the Flemish Institute for Biotechnology. On the other hand, I'm affiliated with the KU Leuven, the largest university within Belgium. The reason for that is that the VIB is using an let's say, mini Howard Hughes medical school type of working, so that we are actually located at the university, but we have a different way of funding and sourcing. So therefore, I have two hats. On the one hand side, the VIB Bioimaging Core. On the other hand, I'm running a KU Leuven departmental core facility, which is called LiMoNe. We have chosen for that name because most of the imaging facilities have, let's say, rather straightforward and boring names like Advanced Imaging Core Facility, which always leads to let's say, simple three-letter acronyms, and in order to have something more open and more recognizable, we chose for light microscopy and imaging network, which is then abbreviated as LiMoNe.